Given a three-phase 480 volt system with a variety of loads, solve for the total complex power. In this case, 480 volts is a line-to-line voltage. We see the first load is a Y-connected, 10 plus J5 per phase load. The next is a delta connected, 12 plus J6 per phase. And the third is power factor correction capacitors with J30 per phase. We're going to use this equation here, which tells us the impedance of a Y circuit is the impedance of a delta circuit divided by 3. And we're going to solve on a per phase basis. And there are multiple ways to solve a three-phase problem. This is the way I think is one of the more straightforward ways to do this. So we start with our source. Recall it was a 480 volt system, so we take 480 and divide it by root 3 to give 277 volts. We're going to assume that's at a phase angle of 0 degrees to simplify the calculation. Our first load, which is the A to neutral, is 10 plus J5. The second load is 4, which is 12 divided by 3, plus J2, which is 6 divided by 3. Again, we divide by 3 based on this equation here. And our third load is the capacitor, and that is negative J10. From there, we can use the tools that we're very familiar with to calculate the total impedance. Keep in mind, though, that this is the impedance for the single phase, because we're solving this on a per phase basis. That calculation tells us that the impedance per phase is 3.5 plus J, 0.5 ohms. From there, we can calculate the line current as the voltage, in this case 277, divided by the phase impedance, which gives us 78 amps at a phase angle of about negative 8.1. Using Eli the Iceman, we see that this is an inductive circuit with a lagging current. We can solve for the complex power in one of three ways. We could say that it's the voltage times the complex conjugate of the current. We could say it's the magnitude of the current squared by the impedance. Or you could say it's the magnitude of the voltage squared divided by the complex conjugate of the impedance. For this example, I'll just use the first calculation. So complex power is equal to the voltage, which in this case is 277 volts at a phase angle of 0 degrees, multiplied by the current, which is 7.8 at a phase angle of negative 8.3. But you'll notice we're using a positive angle because we're taking the complex conjugate of the current. Solving for S, we see that that's 21.4 plus J3 kVA. If we sketch out the power triangle, the real power is 24.4 kW, 3 kVARs, an angle of 8.1 degrees. Here the power triangle pointing up implies that it's inductive, and the apparent power of 21.7 kVA. Now be careful. Be real careful here. Remember, this was on a per phase basis, so this is the little triangle. You could think of this as the power triangle representing the power in one of the three wires. At this point, I like to draw three little triangles just to remind myself what I'm doing, and we take those three little triangles and we put them together to make the large power triangle, which represents the total power in all three phases. Solving for that, we end up with 64 kilowatts and 9.2 kVARs as our total system load. Before we end, we should review those steps one more time. So given a three-phase system with multiple loads, I would encourage you to convert everything to a per phase basis. Again, you don't need to. There are multiple ways of solving this particular problem, but I found this to be a relatively straightforward way to do it. Now, again, a per phase basis with a Y connection. We need to remember that the impedance of a Y circuit is the impedance of the delta divided by 3. We need to remember that the voltage line to neutral is the voltage line to line divided by root 3. By the way, classic mistakes in three-phase circuits is you'll get root 3 and 3 mixed up. And then to make things even worse, if you start playing with RMS values, you can now get square root of 2 mixed up with square root of 3 mixed up with 3. But that's another story. Anyway, from there, solve your per phase complex current and power. To simplify everything, we're going to assume that the A to neutral phase has an angle of 0 degrees. Remember our complex power calculations. So S is equal to VI complex conjugate, or the magnitude of the current squared by the impedance, or the magnitude of the voltage squared divided by the complex conjugate of the impedance. Once that's done, you can then convert everything back into a three-phase system. Your complex power, in this case, would be multiplied by 3.